right, so we've talked about how heat can make a material expand, but also heat can be stored in a material. We already said that in a solid that we can think of connecting these atoms is going to be springs. And then we mentioned that if you take a slingshot and then you pull it a certain distance, it takes a certain energy to do it, but if you pull it back further, it takes more energy. So energy can be stored in the vibrations of materials. And so in this case, you could have vibrations that are going like this. You could also have vibrations that are going like this. And then you could have another atom, let's say another atom is here, and there's a spring attaching those two. So you could have an atom that is vibrating like this. So for each kind of vibration that a material can have, it's going to store a certain amount of energy. Now, in the case of a water molecule, water can store it in a lot of different ways. So here's the oxygen, and then here's the two hydrogens. So you can obviously see that it could be stretching like this. So that would be one kind of energy that the water molecule could store. But can you also see that it could be doing this? So it could be behaving like a spring and stretching like that. So it can store more energy in that kind of vibration. Another way of storing energy is rotational motion. So if you remember in our video, when we talked about energy, there was the energy of a spring, and so that was going to be equal to 1/2, and then it was the spring constant, and then how far did it stretch. Then there was another kind of energy, which was rotational kinetic energy. So when something is spinning, it can have rotational kinetic energy. And so that was equal to 1/2, and then it was its moment of inertia I, which depended on the mass of the object, it depended on the shape of the object, it depended on how it was spinning, and then it depended on how fast it was spinning, and so this was called rotational speed. And then there was another kind of energy, and so this one was linear energy. So linear kinetic energy was 1/2, and then the mass, and then its linear velocity squared. So that substances can have different ways of storing energy. They can store energy in the form of vibrations, energy in the form of rotations, and then energy just because that they're moving in different directions. And water can do all three. So water can be vibrating, water can be rotating, and water can be moving around, bumping into each other. So water has one of the highest, it's going to be called specific heats, and it is the amount of energy that this particular substance can store as you increase its temperature. And water has one of the highest specific heats because it's got all of these different ways of storing energy. So here's our formula. Q is going to be the amount of energy in the form of heat that we're going to put into the substance. And then it's going to depend on what is the substance made of. So that's going to be its specific heat. It's a constant. So water has a certain specific heat, and then steel has a certain specific heat. So different substances have different constants. Then it's going to depend on the mass. So how much of the material do you have? And then it's also going to depend on how much does the temperature of the substance change. So we have this working formula here. So here is some specific heats of different substances. And notice that water in the form of a liquid has a very high specific heat compared to other kinds of substances. And that's because it has so many different ways of storing its energy. So here's a sample question. You have a piece of iron with a mass of 60 grams, and it initially has a temperature of 70 degrees Celsius. It then cools down to 50 degrees Celsius. How much heat did it lose when that happened? So the mass is 60 grams, but notice that's the wrong unit. So we have to convert from grams to kilograms. Then the initial temperature was 70, the final temperature is 50. We're trying to figure out how much heat did it lose. So we're going to use equation 13.2, find iron in our chart of specific heats, and then plug all those numbers in there, and it turns out to be negative 540 joules. So what's the significance of the negative sign? That meant it lost heat when it did that. So that's the negative sign in there. Okay, and then here is another one that is done quite often in chemistry. So you have a piece of brass that has a mass of 40 grams, and it has an initial temperature of 100 degrees Celsius. Okay, you're going to put it into 300 grams of water, which has an initial temperature of 20 degrees Celsius. What will be the final temperature of the water? So you can imagine that the brass is going to cool off, the water is going to heat up. So what we want to know is what's the final temperature of that water going to be. So we're going to write down what we're given and what we're looking for. So we know the mass of the brass, and we're going to write that in kilograms, the mass of the water in kilograms, the initial temperature of the brass, the initial temperature of the water, and then the goal is to find the final temperature of both the brass and the water. So when it comes to equilibrium, the brass is going to cool down, the water is going to heat up until they're both at the same temperature. So that's going to be the final temperature of both the brass and the water. So we're going to take all this information and put it into equation 13.2. So notice that the heat lost by the brass has to go into the water. And so the heat lost by the brass is going to be equal to the amount of heat gained by the water. So now we're going to write down this formula that Q is equal to mc delta T. We're going to write that on both sides of the equation. So on the left-hand side, that's going to be the Q for the brass. On the right-hand side, that's going to be the Q for the water. And notice that one side has a negative and the other side has a positive sign. And why? Because we said that when something gives off heat, that's a negative number. And when something gains heat, that's a positive number. So don't forget to put that negative sign in there. So now it's just a matter of plugging numbers into it and then doing algebra on it. So I'll let you do the algebra. And it turns out that the final temperature of the water is going to be 21 degrees Celsius. So did you notice it started at 20 and it ended up at 21? So the temperature of the water did not change by so much because of the tremendous mass of the water and the high specific heat of the water. So notice that if this is a very, very big number, then this thing over here compensates by being a very small number. Okay, let's take a break and let's apply this to climate.